We can also describe the series written out with the the ellipses and the pluses, or we can describe it as a general term. And we'll see this more when we get to part 2, when we start testing for where the series will converge. And when I say converge, okay, here, what I mean is where the series described with an infinite sum and the actual function match, where they line up. Okay, for some functions, that's everywhere. Okay, for some functions, that's only in a little place, but the most important part is that every series converges at the center. And that's specifically because our series, the series we're going to create, are dependent on a point of tangency. So the function and its tangent function, I guess, tangent polynomial, have to touch, by definition, at that center C, a point of our choice. Okay, so that's good to remind you of. There are 3 options for where a series will converge, where a series and the polynomial it represents match up. Okay, one is that it only converges at the center. That's possible. Okay, only at the center. 2, it only exists in some kind of window. So if I make an illustration of this window, I could say that, okay, here is the kind of the timeline, the X, here is the center C, okay, and it converges for some radius around C. Okay, so if I were to describe this in an inequality, I would say that the X values for which it converges are less than, or, let me be a little more restrictive here, because we're also going to have to test endpoints in the future. So right now, all I'll say is less than the center plus the radius, but greater than the center minus the radius. Okay. All right, or final possibility, converges for all real numbers. And this is the one that we're going to deal with today. We're going to deal with a couple of series that converge for all real numbers. This number r, let's go back to case 2, is called the radius of convergence because it is equal distance around an equal distance around C for which the series will converge. If we have case 1 where it only converges at C, then r is 0. If we have case 3 where it converges for all real numbers, the radius is infinite. Okay, and then later we'll talk about how to deal with the interval of convergence. Okay, but right now I just wanted to introduce this, kind of like we introduced error last time, because I want you to know that the series we're about to create actually fall under case 3. They converge for all real numbers. Okay, one other thing to remember before we move on, the difference between what we did last time and what we're doing right now. Yeah, there we go. Okay, is that a function can be approximated by a Taylor polynomial. Okay, but a function is equal to its series representation, which I will represent using the general formula for series found above. Okay, so the function is approximately the Taylor polynomial because the Taylor polynomial stops. It does not have an infinite number of terms, but the function is exactly equal to the power series that represents it. Okay, so let's go ahead and look at lesson 4. You know, lesson 3 was super short. But lesson 4 is where we get to the good stuff. Okay, so last time, again, we did a Taylor polynomial. Today, we are doing a Taylor series centered. There is no difference, if you want to go back, pause here, and compare the two formulas. There's no difference in the formulas, except that here we have ellipses indicating an infinite number of terms. Okay? And we have what we call the general formula here. Okay? All right, so how do we figure out the general formula? Oh, and one more note, if the center is 0, we still call it a Maclaurin series. That's not different. All right, well, this is going to be all about looking for patterns. So if I want to find a Taylor series for the function e to the 5x, centered at c equals 2, okay, generally they'll ask you for the first number of terms, usually non-zero, in case we're dealing with something like sine or cosine, where some of the derivatives are 0, and then the general term. And that's the part that's, I feel like, most difficult to figure out. But it helps to look for patterns. So remember, if I'm going to write a Taylor series, the first thing I need to do is take the right number of derivatives. So this will be my first term, okay, or will help me find my first term. The first derivative, 5e to the 5x, will help me find my second term. The second derivative, 25e to the 5x, will help me find my third term. And finally, the third derivative will help me find my 125, there we go, fourth term. And remember, I wanted 4 non-zero terms. Now I have to evaluate all of these at the center. So f of 2 is e to the 10th. F prime of 2 is 5e to the 10th. F double prime of 2 is 25e to the 10th. And finally, the third derivative at 2 is 125e to the 10th. Okay, so if I'm writing my power series out, I can write that f of x is equal to, or I can write e to the 5x is equal to, okay, my first term, okay, sorry, I just wanted to focus there. My first term will be f of 2, so e to the 10th. My second term will be the derivative, first derivative, times x minus 2. Okay, my third term will be 25e to the 10th times x minus 2 squared over 2 factorial. And my fourth term will be 125e to the 10th times x minus 2 to the third over 3 factorial. And here comes the fun part, the general term. Here is my hint. Okay, think about, instead of this being like first term, second term, third term, I want you to think about this starting to like renumber all of the terms. If they're all non-zero, we're going to renumber them. This is going to be when n equals 0. Okay. This one is going to be n equals 1, n equals 2, and n equals 3. This kind of helps us match up what n we're going to plug into our general formula to get this term out. So one thing I notice is that every time I have a new term, I multiply by another 5. So I have 5 to the n. So 5 to the 0 is 1, which is why I have no 5s here. 5 to the 1 is 5. 5 squared is 25. 5 cubed is 125. Okay? I notice that I always have an e to the 10th. That doesn't seem to matter, so I will make sure to multiply my general term by e to the 10th. Okay? The next thing I notice is that the exponents on 5 match the exponents on the x minus 2 terms. So I will also say that this is x minus 2 to the nth power. And finally, my n's match the factorials in the denominator, so I will write over n factorial. And I missed out on a little room here, but at the end I'm going to write plus dot 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 to indicate that this keeps going. Okay, so I'm just, in order to write the general term, I'm just looking for patterns in the first couple of terms that I write out. Okay, so let's practice this some more with some very special series. And these are special because, again, they converge for all real numbers. So down here where it says 4, I'm going to write the interval of convergence is negative infinity to infinity. Okay, we can prove this later on, but for now we're just going to say that this is a given. Okay, proving that it comes in part 2. All right, so if I want to derive a series for e to the x, the good news is, oh, and excuse me, I would like to derive a Maclaurin series. So that indicates to me that my center is 0. Okay, so if I'm going to derive the series, I need to write at least the first 4 terms non-zero and the general term. So f of x is e to the x, f prime of x is e to the x, f double prime of x is e to the x, and the third derivative is e to the x. Okay? All of these are equal to the same thing when I plug in 0, and that thing is 1. So f of 0 is 1, f prime of 0 is 1, f double prime of 0 is 1, and third derivative at 0 is 1. Okay, so we're ready. Alright, my first term, let's scoot this up. My first term is f of 0, 1, plus 1 times x. Remember, I'm not doing x minus 0 just to simplify it. Okay? Plus 1x squared over 2 factorial. Plus 1x cubed over 3 factorial. Now, do you really need all those ones? No. Plus 1, 2, 3. Okay, let's look at our general term. Again, it's going to be n equals 0, n equals 1, n equals 2, and n equals 3. Well, there's not a lot to this pattern. I know that my n's match both the factorials and the exponents on x. So I'm going to say that the general term is x to the n over n factorial. And that's it. Okay? Here is our power series for e to the x. Okay, let's try the same thing for sine. Okay, and we did sine, we at least worked with sine the other day. Sorry, let me scoot this forward. Okay, we worked with sine the other day, so we know that some of those derivatives are going to be 0. Okay, but let's try to, I'm going to write out all the terms, even if, okay, actually I'm going to, excuse me, that's not what I want. I'm going to write out all the terms, but I'm going to write out even more terms than I usually would, just so I can observe a pattern with more than 2 samples. So, because I know, okay, that f of x is sine x, the first derivative is cosine of x, but here's where I start getting into sign changes. The second derivative is negative sine of x, the third derivative is negative cosine of x, and by the fourth derivative we come full circle and I get sine of x again. Okay, I'm going to do 2 more, let's see. The fifth derivative is cosine. Okay. The sixth derivative is negative sine. And the seventh derivative is negative cosine of x. Now, I don't have to worry about the ones that are going to be 0. Okay, so I'm just going to say that f prime of 0, because remember I'm looking for a Maclaurin series, is 1. F triple prime of 0 is negative 1. The fifth derivative at 0 is 1. And the seventh derivative at 0 is 1. Okay. Everything else, all of these other derivatives will be 0 because sine of 0 is 0. Alright, so I'm going to write this out before I write it in my nice pretty box here. Okay, again, this series is going to converge from negative infinity to infinity. Okay, I'm giving you this now. We're going to prove it in part 2 of chapter 9. Okay, I'm just going to write the non-zero terms. Okay, so this would be term number 1, not existent. Term number 2 is the derivative. Okay, so sine of x equal to the derivative 1 times x to the first. Okay, I skip the second term, the second derivative, move to the third derivative. Negative 1 x cubed over 3 factorial. Skip the fourth derivative, 1 x to the fifth over 5 factorial. Oops, I forgot a negative here, didn't I? This is why it pays to write stuff out. Okay, 7th minus 1 x to the 7th over 7 factorial. So because all of the even derivatives, and including the first term, are 0, we're only getting the odd exponents. We're only getting the first, the second, the third, the fourth. So I need to find a way to create odd integers only. Okay, and this is where it helps to relabel this as n equals 0, n equals 1, n equals 2, n equals 3. Because I think it's much more helpful to think about this being just directly in order than it would be to try to get some series to skip numbers. So if I think about this as n equals 0, okay, that means I need a formula that when I plug 0 in will not just give me 0 as the exponent for x. And this is where it might help to have a little background knowledge. How do I create odd numbers? Well, all of the even numbers, in fact, okay, the definition of being an even number is that it's divisible by 2. So all the even numbers can be written as 2 times n, where n is an integer. And that's the fancy symbol for all the integers. Sorry, I kind of messed it up there. All the odd numbers are 1 away from the even numbers. So all the odd numbers could be 2n plus 1, where n is an integer. Okay? So if I want odd exponents on x, I'm going to let my x term be to the 2n plus 1. Okay, and that exponent has to match my factorial, so I will put 2n plus 1 factorial. Make sure you use these parentheses, because if you don't, that factorial only applies to the 1. Okay, so if you want to apply the factorial to the whole thing, you need to put parentheses that way. Okay, now should I do 2n plus 1 for the alternating sign that I see here? No, because it happens every other time. And think about this, if I square a negative 1, okay, I will get rid of the negative 1. Sorry, I don't know why that took me so long to process. So if all of the even n's are supposed to be positive, okay, why don't I just let the exponent on negative 1 be n? Okay, because for n equals 0, well, anything to the 0th power is 1. For n equals 1, I'll get my negative 1. For n equals 2, I'll square it and I'll get back to positive 1. N equals 3, it's odd again, back to negative 1. Okay, so I can leave my exponent for negative 1, the alternating signs, as just n. So if I want to clean this up a little bit, write my final formula, I'll write that sine of x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus negative 1 to the nth power x to the 2n plus 1 power divided by 2n plus 1 factorial. And there it is. There's a generic formula for sine of x. Also worth remembering. How do you remember, though, that sine has all the odd exponents? Well, if you think about the symmetry of sine, it's symmetric, at least for some part, about the origin, right? So you can think about sine having odd powers. Okay? Hopefully that gives you a hint as to what cosine will be, but I'm going to leave you to derive this one by yourself and check your work with the filled notes, because I want to move on to what can we do with these power series once we have them. The reason they make everything easier is we can then manipulate them to do other things. Okay, so we can substitute things into the series, meaning do a composition. Okay. Okay, like that example we did the other day. We can multiply or divide, okay, by a constant or a variable to get a new function. We can add or subtract two series, which is actually how you prove Euler's identity, which we will do. Okay. Or you can differentiate and integrate a series and that's part of what we brought up at the beginning. Doing it just requires the power rule for each separate term. Okay, so let's do a couple examples. If I want to find the Maclaurin series for sine of x squared, the first thing I want to do is write down the Maclaurin series for sine of x. So sine of x is equal to what we just derived. Okay, so x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and the general term, negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. If I want to find sine of x squared, all I have to do is replace all of the x's with x squareds. It's a composition of functions. So sine of x squared is equal to x squared, plus, dang it, minus x squared cubed over 3 factorial plus x squared to the 5th over 5 factorial minus x squared to the 7th over 7 factorial. And replacing in the general term works just like it does in the regular function. I am just replacing x with x squared. Notice that doing it this way will also help. We don't have to redefine the general term if we just do replacement. Keep my formatting up. Okay, so our final answer, if we want to simplify all the exponents, would be x squared minus, okay, what happens when you raise an exponent to another exponent? You multiply them. So x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial. The general term, okay, would be x to the 4n plus 2, because you have to distribute this exponent to the 2n and to the 1, over 2n plus 1 factorial. Okay, so a totally new function that if we really didn't know anything about, we might struggle to find the series for, especially since taking the derivative would be exhausting. Okay, but if I can use something I already know, I can just do composition. And then I can build off of that. If I would like to find a Maclaurin series for the derivative of f prime of x, which, remember, f of x is sine of x squared. So we want to find a Maclaurin series for the derivative of this. Well, in order to find f prime of x from here, I would just take the derivative. But if this is equal to this, I can just take the derivative of this. Okay, so the derivative is equal to the derivative of sine of x squared. Okay, and I'm just going to do the power rule with this, what I just wrote right here. So I would get 2x minus 6x to the 5th over 3 factorial plus 10x to the 9th over 5 factorial minus 14x to the 13th over 7 factorial. When I'm going to run out of space, I'm going to put the general term right here. Okay, I've still got my negative 1 to the n, but then I've got 4n plus 2, okay, times x to the 4n plus 1, because I subtracted 1 from the exponent, okay, all over 2n plus 1 factorial. Okay, and that's it. You can simplify some of those coefficients if you would like, but you don't really have to. That is a power series for the derivative of sine of x squared. Okay. All right, so let's do 2 more, and then we'll be done. Okay, so example 2. Find the Maclaurin series for x times cosine of x. All right, well, this is the one I didn't derive for you. So if you haven't already derived the series for cosine of x, stop right here and go back. Okay. If you are back now and you have derived the power series, you should have gotten cosine of x is equal to all of the even terms. So 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. Okay, general term looks very similar to sine, negative 1 to the n, but now we have even exponents. Okay, and an even factorial. Okay, this is for cosine of x. In order to transform cosine of x into x cosine of x, I would just multiply by x. So if I want to transform this series into the series representing x cosine of x, I just multiply by x. Okay, which is really nice. So x cosine of x is multiplying each of these individually by x. So x minus x cubed over 2 factorial plus x to the 5th over 4 factorial minus x 7th over 6 factorial. Okay, and then negative 1 to the n, x to the 2n plus 1. Ooh, 2n plus 1, that's how we get all of our odd factorial, or excuse me, that's how we get our odd numbers. But notice, just because we multiply by x doesn't mean anything else changes. Okay, it doesn't mean that it changes into like a new series. It doesn't mean it's equal to sine, especially since all of the factorials are still even. Okay, we need to multiply by more than that to get the series for sine. Okay, but you're allowed to just multiply by an x. You're allowed to multiply by a constant if you would like, either way. All right, but let's see what we can do with this. So use your answer to find the Maclaurin series for the integral from 0 to x of f of t. Let me write out what that might mean. So they want the integral from 0 to x, and remember we're using t here because if we want to integrate from 0 to some upper unknown bound, that is x, okay, we can't use x here and x in the function, but f of x is t cosine of t. Okay, we would like to find the Maclaurin series for this. Do I want to integrate this? No, I do not, because that would be kind of confusing. Well, we could use integration by parts, but then after we use integration by parts, we have to create a new series for each component of the integration by parts. So let's just use what we did above, okay, where we had a power series that represented x cosine of x, okay, and let's sub that in. Let's let that be our representation. So if I sub it in using all t's, I can say that this was equal to the integral from 0 to x of this function. But remember, instead of writing x, we have to write t, okay, just for notation. Okay, so I've got t minus t cubed over 2 factorial plus t to the 5th over 4 factorial minus t to the 7th over 6 factorial. Tempting to make them match. Make sure you're paying attention when you're writing. Okay, and I have to include my general term. So negative 1 to the n, x, nope, t, got him, t to the 2n plus 1 over 2n factorial. And all of this is being integrated with respect to t. Okay, so this looks like we're about to do the second fundamental theorem of calculus where we take a derivative, but we actually do want to integrate it this time. Okay, so if I integrate everything, and it is a definite integral, I do have bounds, okay, no plus c, I get t squared over 2 minus t to the 4th over 4 times 2 factorial. Notice that just as I wrote 4 times 2 factorial does not mean that factorial applies to that 4. It only still applies to the 2. Plus t to the 6th over 6 times 4 factorial minus t to the 8th over 8 times 6 factorial. General term time, I still have negative 1 to the n, but now I have t to the 2n plus 2, okay, so more even numbers, divided by 2n plus 2, and let me use some parentheses, 2n factorial. This is being evaluated from 0 to x. It's important that you remember to write the 0 and not just immediately sub in the x, just in case for whatever reason, if we have started with the term, started with some kind of, or we did have some kind of constant, excuse me, or if we somehow in our series we needed to plug in 0, and we would get real constants out, just make sure you write the 0 so you remember to plug it in. It's not common that you would have to actually write something out, but just in case. Okay, but now, in this case, when we sub in x for all of them and subtract when we sub in 0 for all of them. So when I sub in x, I get x squared over 2 minus x to the 4th over 4 times 2 factorial plus x to the 6th over 6 times 4 factorial minus x to the 8th over 8 times 6 factorial. My general term, negative 1 to the n, x to the 2n plus 2 over 2n plus 2 times 2n factorial. And I didn't write anything else because when I subbed in 0 for each of these t's, I got 0. So that's it. That's our power series that is representative of this integral. Okay, but that's it for lesson 3 and 4, actually. Yep, 3 and 4. So you have 2 more worksheets. One worksheet on power series, okay, with an AP problem at the end. Ooh, volume by rotation. Okay. Actually, I think it's just one worksheet. I think you just have worksheet 1 on power series. That's it. So make sure that you're working on that. If you have time in class, do that so that you're prepared. You don't have to do it at home. You can ask questions to your peers. But if you still have questions, make sure to give me a text or let me know when I get back.